So in this lesson, we will be talking about infinite sums of numbers. So the previous lesson was infinite lists, and what we're going to talk about here is what if we take the numbers in those lists and add them up? Is it possible that an infinite number of things could add up to a finite number? So let's consider this question. How might you define the sum of an infinite number of things? And then, is it even possible that an infinite number of things could add to a finite number? So let's consider Zeno's paradox and spring break. So this is you, and over here is your next break. It could be spring break, or it could be Christmas break. It just depends. But there's your, we'll just say it's spring break. And we'll just call that a distance of 1 unit. You're going to get there by first going halfway, and then half of what's left, or a quarter, and half of that half, or an eighth, and then a 16th, a 32nd, etc. And I think it should be pretty obvious that this 1/2 plus this 1/4 plus this 1/8 plus this 1/16, etc. should eventually add up to your 1 total unit away you are. So now the question is how would you define adding up an infinite number of things? And here is the general strategy. Suppose you have a sum from n equals 1 to infinity of an. So that's a1 plus a2 up to an, and then you just keep going. So you want to add an infinite number of things, and the question is how would you do that? So what you do is you say, well, I can add a finite number of things. So you make these things called partial sums. S1 is the first partial sum, it's just your first term. S2 is the second partial sum, it's your first term plus your second term. S3 is the sum of the first 3 terms. And then Sn will be the sum of your first n terms. And this makes a series into a sequence or a list of partial sums, S sub n's. And if these S sub n's, if that sequence converges, then the series converges to the same value. So for now, what we're going to do to determine if a series or an infinite sum converges is find a list, find a sequence of the partial sums, and show that that converges using what we know from the previous lesson. So here is that definition stated more formally. If you have an infinite series from n equals 1 to infinity, adding up the a sub n's, the nth partial sum is given by adding up the first n terms. And if the sequence of partial sums converges to something, some place S, then the infinite sum also converges to S, and we say that the sum is equal to S. If your sequence of partial sums diverges, then your series also diverges. Okay, so this series, this is the series that is 1/2 plus 1/4 plus 1/8, etc., plus 1/2 to the n, and keeps going. As we discussed, this series is going to add to 1. That was the exact same series we had with the Zeno's paradox and your upcoming break. All right, for this one, let's try to get an expression for the nth partial sum. So start by plugging in 1. Some kind of pattern is going to emerge here. We get 1 minus 1/2. That's what we get when we plug in 1. Now when you plug in 2, you get 1/2 minus 1/3. When you plug in 3, you get 1/3 minus 1/4. And you can see that some stuff's happening here. this negative 1/2 and that 1/2 are canceling. This negative 1/3 and that 1/3 are canceling. The 1/4 will cancel the second I write down the next term. So the last term in your partial sum will be 1 over n minus 1 over n plus 1. One prior to that will be 1 over n minus 1 minus 1 over n. And notice that this 1 over n and that 1 over n will cancel, but from that point prior, all the denominators are decreasing, so no one's going to cancel with this 1 over n plus 1. So an expression for our nth partial sum, S sub n, is 1 minus 1 over n plus 1. This would be a way to have a shortcut to, say, add up the first 100 things in that series. If you want to add up the first 100 things, well, then just plug 100 into this formula. First 1,000 things, plug in 1,000. Now that infinite sum will equal the limit as n goes to infinity of the sequence of partial sums. So take the number of things that you add up to infinity, and you can see that this limit is equal to 1. So thus our series, our original series, converges to 1, or adds up to 1. Now, what is meant by the sum from n equals 1 to infinity of 1? Well, what this means is 1 plus 1 plus 1 plus, etc. 1, adding 1 repeatedly forever and ever and ever. So an expression for the nth partial sum means you add 1 to itself n times, which is the same thing as n times 1, or n. So thus the limit as n goes to infinity of Sn is the limit as n goes to infinity of n, and it's equal to infinity. So this series diverges. All right, the sum from n equals 1 to infinity of n squared. Well, this is 1 plus 2 squared, or 4, plus 3 squared, or 9, etc., up to n squared. So I think it's pretty obvious here. So we have S sub n is 1 plus 2 squared all the way up to n squared. As n goes to infinity, these S sub n's are going to go to infinity as well. So thus this series diverges. So one of the previous examples that we had was an example of something called a telescoping series, where alternating terms are canceling. So for this one, you see that this b2 that's negative cancels that b2, and this one will cancel with that one, etc. Okay, so what we're going to also do is discuss another telescoping series where you have to make it into the form that telescopes. So find the sum of this series. So we're going to use our partial fraction decomposition to decompose 2 over n plus 1 times n minus 1. And that will equal, we'll say, a over n plus 1 plus b over n minus 1. Now we multiply by n plus 1 times n minus 1, which gives us 2 equals a times n minus 1 plus b times n plus 1. When you input n equals 1, you get that 2 equals 2b, therefore b will equal 1. And when you input n equals negative 1, you get that 2 equals negative 2a, and therefore a is negative 1. So now using that information, let's rewrite the series as a sum from n equals 2 to infinity. I'm going to actually put the one with the b first because it's positive. So that will be 1 over n minus 1 minus 1 over n plus 1. If you want to be 100% certain that you're correct, you could get a common denominator, and those two expressions should add up to 2 over n squared minus 1. Okay, so whenever you have a telescoping series, I need you to give me a clear expression for the nth partial sum. So Sn will equal, now first we plug in 2. When we input 2, that first term is 1, and the second term is 1/3. When we input 3, because our first input was 2, we have 1/2 minus 1/4. And for a second you feel cheated because I told you it was telescoping. There's no canceling yet. So, well, don't lose hope, just put one more term down. So we did n equals 2, n equals 3, n equals 4 will give us 1/3 minus 1/5. And notice now that this negative 1/3 will cancel with that 1/3. If I wrote down one more term, my next term would be 1/4 minus 1/6. Notice that that 1/4 will cancel with that 1/4. We're good. Nothing will cancel the 1, nothing will cancel the 1/2. So we figured out what terms are left from the beginning. I'm just going to underline them so I can't lose track of them. So this one's going to stay, this one's going to stay. Now on the end, the last term we have is 1 over n minus 1, 1 over n plus 1. That should be a minus between the two of them. Now one previous will be 1 over n, 1 over n minus 2, no obvious canceling. One more previous, 1 over n minus 1, 1 over n minus 3. And we can see then that this 1 over n minus 1 will cancel with that one. I go one term previous, this guy will cancel. What does not cancel is this 1 over n, and that 1 over n plus 1. So Sn will be 1 plus 1/2 minus 1 over n minus 1 over n plus 1. Or 3/2 minus 1 over n minus 1 over n plus 1. And as n goes to infinity, the partial sums, the s sub n's, are going to go to 3/2. So your series converges to 3 over 2. Now another common series we can actually find the sum of is the geometric series. So a geometric series is given by a sum from n equals 0 to infinity, ar to the n. So we have something raised to the nth power. So sort of like a constant multiplier, and then some constant a. And a geometric series with ratio r diverges if the absolute value of that r is bigger than or equal to 1. And it converges if the absolute value of that r is in between 0, but strictly less than 1. And let's actually prove why that works. So the nth partial sum, Sn, note here that this sum begins at 0. Your current textbook does define this sum at 1 and does it a little bit differently. I think that summing from 0 actually is easier, so I'm going to diverge from your textbook a little bit in this lesson. Okay, so Sn, the nth partial sum, first you plug in 0, you get ar to the 0, so that's a times 1, or a, plus ar squared, all the way up to ar to the n. So that's Sn. Now we're going to do a clever trick. We're going to multiply Sn by r. So Sn will equal ar plus ar squared plus ar to the n, and it'll have one more term that's ar to the n plus 1. And now we're going to find s sub n minus r s sub n. So if you take this top line minus this bottom line, all these terms in the middle are going to cancel out, just leaving you with a minus a times r to the n plus 1. Now take out the nth partial sum expression, s sub n, 1 minus r equals a times the quantity, 1 minus r to the n plus 1. And so an expression for the nth partial sum is a times the quantity, 1 minus r to the n plus 1, all over 1 minus r. And now if your r is bigger than 1, r to the n plus 1 is going to go to infinity. Think about this. If you take like something like 2 and raise 2 to a power, that's going to get bigger and bigger and bigger. It's exponential growth. That's also true if you have something like 1.1 to the power of n. That's also exponential growth. So this thing will increase. If your r is less than 1, but also, well, we'll say its absolute value, then r to the n plus 1 is going to go to 0. And then s sub n will converge to a over 1 minus r. If r is actually equal to 1, what you will have here is a sum from n equals 0 to infinity of a times 1 to the n, or just a sum from n equals 0 to infinity of a. So a plus a plus a plus a forever and ever and ever. That's also going to diverge. So this is what a geometric partial sum will add up to. Now one thing to note is that is a formula that specifically applies when the lower bound is 0. If that lower bound is not 0, you've got to mess around with the series a little bit to make it into 0 by doing something called reindexing, which we'll also discuss. Okay, so tell me whether the following series converge or diverge. And if the series converges, find what it converges to. So a good idea, a good hint this is a candidate for being a geometric series is that you have 3 to the n power in a denominator. So think this is the same thing as n equals 0 to infinity, 5 times 1/3 to the n. So that is a geometric series. And your a is 5, and your r is 1/3. So as the absolute value of r is less than 1, this thing is going to converge. And it will converge to a over 1 minus r. Note our sum begins at 0, so that means we can use that formula without any other hassle. So we'll have 5 over 1 minus 1/3. Simplify that by multiplying the numerator by 3, the denominator by 3, which makes that 15 over 3 minus 1, or 15 halves. So that series will add up to 15 halves. Now this next one, we have the sum from n equals 1 to infinity of 5 over pi to the n. Okay, so first let's think about what this would look like. We have 5 over pi plus 5 over pi squared plus 5 over pi cubed, etc. The first problem I have is that this series begins at 1, and if I want to apply a geometric series formula, it has to begin at 0. So we'll say sum from n equals 0 to infinity. The 5 can just hang out, but what you need is you need the power on that pi to be 1 when you plug in 0. You need to be 2 when you plug in 1. So when you input 0, you need to get out a 1. When you input 1, you need to get out a 2. So your exponent here will have to be n plus 1. So if you decrease where you start, you have to increase the exponent. Now that will simplify to the sum from n equals 0 to infinity 5 times 1 over pi times 1 over pi to the n. You can also note that, like, if I had to change that from n equals 2 to n equals 0, the power here would have been n plus 2. So note that this is also geometric. The a is actually 5 over pi, and the r is 1 over pi. And since pi is about 3.14, 1 over 3.14 is certainly less than 1. So this thing will converge to a over 1 minus r. So 5 over pi over 1 minus 1 over pi. Multiply numerator and denominator by pi to simplify. And we have that this series sums to 5 over pi minus 1. This will involve some pre-processing before we're able to figure out if this converges or diverges. So first of all, begins at 0, so no re-indexing necessary. Let's write this as 3 times 3 to the n over negative 2 to the n, which is the same thing as the sum from n equals 0 to infinity 3 times negative 3 halves to the n. So in this case, we have a equals 3 and r equals negative 3 over 2. As the absolute value of negative 3 over 2 is bigger than 1, this geometric series will diverge. Oh man, here re-indexing necessary, but before I do that, I'm going to do some other simplifications. So sum n equals 1 to infinity, we'll have 6 times 2 to the 2n times 2 to the negative first over 3 to the n. So that's just exponent rules. When you multiply things with common bases, the exponents add. I sort of undid that step. This becomes the sum from n equals 1 to infinity. 6 times that 2 to the 2n is the same thing as 4 to the n over 3 to the n times 2. Now that 6 over 2 can reduce to 3. And we'll have 4/3 to the n. Technically, you could tell at this step that your series is going to diverge because 4/3 is the r and it's bigger than 1. But I would like to make sure you know how to re-index. Let's actually do that. Sum from n equals 0 to infinity 3 times 4/3 to the n plus 1. So that's the same thing as the sum from n equals 0 to infinity 3 times 4/3 times 4/3 to the n. So the a would equal 4 in this geometric series, and the r will equal 4/3. And as r is bigger than 1, this series diverges. You can also use infinite series to convert repeating decimals back into fractions. You learned way back in the day probably that every rational number is a number with a decimal expansion that either terminates or repeats, which means you can write every repeating decimal as a ratio of two integers or as a fraction. So you can actually prove this using algebra, and it's kind of a clever trick. So let x equal 0.4646, etc. I'm going to multiply my x by 100. 100x will equal 46.46. 0.46, etc. Then 100x minus x will equal just 46. So 99x equals 46, and x will equal 46 over 99. And notice x was equal to that decimal. So that's one way to, say, show that the number 0.46 is equal to 46/99. Now another way is to use a geometric series. And it's a little bit more complicated, but I think it's important to see how this relates to the idea we're discussing. So how you can think about this as a geometric series is you can think about 0.46, 46, 46, etc. first as 46 over 100. That's what those two first places are. The next two places are 46 in the 10,000th place, etc. So you can think about this as 46 over 100 to the first, 46 over 100 to the second, etc. So that's the same thing as the sum from n equals 1 to infinity of 46 over 100 to the n. I chose on purpose not to try to start at 0 because it's easier to actually re-index this. So this is going to be a geometric series and it is going to converge. So let's re-index sum from n equals 0 to infinity, 46 times 1 over 100 to the n plus 1. So same thing as the sum from n equals 0 to infinity, 46 over 100 times 1 over 100 to the n. And that's a geometric series. Your a is 46 over 100. Your r is 1 over 100, which is certainly less than 1, so that converges. And it converges to a over 1 minus r. So 46 over 100 divided by 1 minus 1 over 100. And that's going to be 46 over 100 minus 1, or 46 over 99. You can use either method for your homework to convert decimals, repeated decimals, back into fractions. I just thought it was important to show you how a decimal expression can be written as a geometric series. All right, how about this series? Is this series convergent or divergent? Well, so let's start by trying to simplify those exponents a tad. So first of all, this 2 to the 2n, that's going to be 4 to the n. And this 3, let's make that 3 to the first and 3 to the negative n. So that becomes the sum from n equals 1 to infinity, 3 times 4 over 3 to the n. And you can tell right now that your r is going to be 4/3, which is bigger than 1, so this thing is going to diverge. But let's just practice re-indexing because it's good to know how to do it. So sum from 0 to infinity, 3 times 4/3 to the n plus 1. And that's the same thing as the sum from 0 to infinity, 3 times 4/3 times 4/3 to the n. So this is a geometric series with a equal to 4 and r equal to 4/3. And as r is bigger than 1, this series diverges. Now, a great way to test if a series is a candidate for convergence is to look at the limit of the things that you're adding up. If the things that you're adding up don't get small, as in don't go to 0 quickly enough, then the sum will be divergent. So what we're going to prove here is that if your series converges, then you can conclude that the limit as n goes to infinity of the ans is 0. Okay, so let's prove that. So if the series converges, so if the series from n equals 1 to infinity of an converges, that means your sequence of partial sums, S sub n, converges. That's by the definition of how we define a series converging. So let's find what S sub n is. S sub n would equal a1 plus a2 up to an. And notice that S sub n minus 1, that would be a1, a2 up to a sub n minus 1. So S sub n minus 1 has one less term in it than S sub n. And if I take S sub n minus S sub n minus 1, so I take this whole thing, take away this thing, notice how everything cancels except for a to the n. So that would equal a to the n. So we know as n goes to infinity, S sub n goes to some number s, because we know that this series converges. And then also, as n minus 1, or we'll say also as n goes to infinity, n minus 1 also goes to infinity. It's just one step behind. And if that's true, we know that s sub n minus 1s, those also have to converge to s. And what this tells us is that a sub n is going to converge to s minus s or 0. Now, one thing that is a common error in classes like this is that students try to confuse this if-then. This says that if the series converges, then the limit of the terms is 0. What it does not say, it does not say if the limit as n goes to infinity of the ans is 0, then your sum converges. That is uber false. Switching the if-then can change the sort of outcome of the situation. So this is something that's called a necessary but not sufficient condition. And what that means in this case specifically is for a series to converge, the a sub n's, or the things you're adding, have to go to 0, but this alone does not imply convergence. Another example of that kind of, this is not to diss on math teachers, but for math teachers, some example of a necessary but not sufficient condition would be you have to know your math, but you also have to be able to explain it. Knowing the math isn't enough to be able to be a, say, good math teacher. There are other examples that also could apply here, but if your series is going to converge, those terms have to go to 0, but just because that happens, it doesn't mean it's enough to imply convergence. And the typical example where the terms go to 0, but the sum does not converge, is the sum from n equals 1 to infinity of 1 over n. So this series diverges even though 1 over n goes to 0. So the idea here is that these terms don't get small quickly enough. And so what we're going to do to prove this is we're going to look at the partial sums s2, s4, s8, etc., all the powers of 2. This series does diverge very slowly, but you can actually prove that it diverges. So notice that S2 will equal 1 over 1 plus 1 over 2, or 3/2. But 1 plus 1 over 2 is what we're going to think about it as. S4 will be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And notice that this is bigger than 1 plus a half plus a quarter plus a quarter, because 1/3 is bigger than a quarter. And that's the same thing as 1 plus 2 over 2. Now S8, that'll be 1 plus a half plus a third plus a quarter plus a fifth plus a sixth. This is going to take a while. Plus a seventh plus an eighth. That's bigger than 1 plus 1/2. The 1/3 plus 1/4 is bigger than a quarter plus a quarter. And this next part is bigger than an eighth plus an eighth plus an eighth plus an eighth. And that equals 1 plus 1/2, 1/2, 1/2 is 3/2. So using the same pattern, we're going to end up with the fact that S16 is bigger than 1 plus 4/2. So in general, the partial sum of 2 to the nth power is bigger than or equal to 1 plus n over 2. Because notice that here, this was 2 to the first, and we had 1/2. 2 to the second, and we had 2/2. 2 to the third, 1 plus 3/2. Okay, so that is it's a subsequence, and as n goes to infinity, S2n goes to infinity also. So thus Sn goes to infinity. And the thing you have to believe is that this is not the entire sequence of partial sums, it's just some of them. And you've got to believe that as that the sort of subsequence, or the sort of not all of the numbers, but as this thing goes to infinity, so must the original sequence. Now you might be thinking, oh my gosh, okay, well, if I can't conclude a series convergence, what good is that theorem? Well, the good is that since you have to have your terms going to 0 for convergence even to be an option, if they don't go to 0, then you know convergence can't happen. So what this will mean, if your limit is not 0, eventually you're adding up numbers that are very near to some non-zero thing, which will eventually be infinite. So when you're looking at a series, the first thing you should always check is is the limit as n goes to infinity of an, is that equal to 0? Yes, no. If yes, you've got to figure out what it converges to, if it converges or not. And at this point in time, the only tools you have are geometric and telescoping series. And if the limit is not 0, so if yes, maybe you'd have a geo, maybe you'll have a telescoping. And if no, well then you know that this thing diverges. So first thing to check, is the limit 0? So let's find the limit as n goes to infinity of n squared plus 1 over 2n squared minus 5. Well, that limit is 1/2, which is not equal to 0. And you say, thus, use your fancy words, the series diverges by the test for divergence. Some books call this the nth term test. I'm okay with either name. Okay, something kind of wacky looking. You're like, oh, ln of weirdness. Well, let's check and see if the ln of weirdness goes to 0. So find the limit as n goes to infinity of ln of strangeness. Well, remember that the limit can move inside the natural log, as natural log is a continuous function. And well, that limit of the expression inside the log will be 5. So you have ln of 5. And I know that that is not equal to 0. And so thus, by the test for divergence, this series diverges. Okay, so that's it for the first lesson on series.